going to be talking about the compatibility of elements during mantle melting. To start off with, we're going to think for a moment about how the continents and the ocean bedrock look. They look quite different, right? Continental rocks are often lighter in color, while ocean bedrock is often quite dark. These rocks look different because they are quite elementally distinct. But how did they get this way? We start our journey down in the mantle. Here we have our model mantle, but something doesn't look quite right. That's much better. We have all sorts of different elements stuffed into the fabric of the mantle, some larger and some smaller, some distorting the fabric more than others. You have to think that each element has sort of a particular personality, and just like people, some are better friends with each other, and some simply cannot wait to leave their home for a space where they better fit in. Let us choose rubidium to be our protagonist today. Say hello, rubidium. We are going to investigate today whether rubidium will choose to go into the melt or stay in the solid when a mantle parcel melts. A useful term to familiarize ourselves with is the partition coefficient, or Kd. This is a value that parameterizes how likely an element is to migrate from the solid into the melt phase. It places the concentration of any element that remains in the solid parent over the concentration of that same element that goes into the melt. The specific Kd for any element depends on the mineralogical composition of the rock you melt, and we like to call elements that prefer going into the melt, meaning a Kd of less than 1, incompatible, and those that prefer to stay in the mineral phase, meaning a Kd greater than 1, compatible. This incompatible and compatible business refers to the element being compatible or incompatible with the parent mineral phase. Let's take a look at the values for rubidium. Are they greater than or less than 1? Our friend rubidium has a Kd far less than 1 for mantle-derived melts, meaning it is simply itching to leave the mantle and swim over into the melt. But why? Well, for starters, rubidium is pretty large. This means it needs a lot of space in a mineral structure to fill up, which is just not available in the magnesium and iron-rich olivine crystal. And secondly, the overall equation guiding whether an element goes into the melt or stays in the solid shows a mutual dependence on the ionic radius and the amount of strain that is exerted by this radius shift on the crystal lattice, as shown by Young's modulus. These two central characteristics determine how happy a rubidium ion, or any ion, will be within any given mineral structure. So let's see how that thermodynamic desire for rubidium to leave the mantle actually manifests on the Earth. Here is a plot of the relative abundance of a variety of elements in the crust, normalized to depleted mantle value, arranged along increasing Kd values. Where is rubidium? All the way up there. Say hello, rubidium. Wow, we can see here that rubidium is substantially enriched in the continental crust relative to the mantle. The moment that rubidium sees the escape door from its olivine and pyroxene neighborhood, it takes it. Each element has its own ranking of comfort/discomfort with mantle minerals that result in each element retaining a unique enrichment ratio. Although almost no elements are as unhappy as rubidium in the mantle, many +1 and large ionic radius elements do find themselves partitioning into the crust rather than staying within the mantle. The difference between different elements' affinity for their mantle original home determines their relative abundances in crustal rocks or mantle-derived rocks, which can in turn make them quite useful for constraining other geological processes. For example, the rubidium-strontium isotope system is made possible by the difference in the abundance of rubidium and strontium in melts from the mantle. And the same applies to samarium and neodymium. These systematics are foundational to understanding continental formation processes and mantle dynamics and setting modern climate and oceanographic elemental distribution patterns. This makes understanding each element's mineralogical personality critical to understanding the foundations of Earth's chemistry.